Ever wondered why some reactions are faster than others? Today we dive into the world of reaction theories. Let's start at the beginning. What exactly are reaction theories? Well, they're theories that help us understand how and why chemical reactions occur at the speeds they do. If you've ever seen a firework explode, a piece of fruit ripen, or a car rust, you've witnessed chemical reactions in action. But what determines how quickly or slowly these reactions happen? That's where reaction theories come in. There are two primary theories that we'll explore today: collision theory and transition state theory. Collision theory, as the name suggests, is based on the idea that for a reaction to occur, particles must collide with each other. But it's not just any old collision that will do. The particles must collide with enough energy and in the correct orientation for a reaction to take place. This theory helps us understand why increasing the temperature or concentration of a reaction can speed it up. Transition state theory, on the other hand, dives deeper into the nitty-gritty details of a reaction. It looks at the very peak of the reaction process, the moment when old bonds are breaking and new ones are forming. This fleeting moment is known as the transition state. According to this theory, the speed of a reaction depends on how quickly molecules can reach this transition state. So why are these theories important? Well, they give us a framework to understand the speed and mechanisms of chemical reactions. By understanding these theories, we can predict how changes in conditions like temperature and pressure will affect the rate of a reaction. This knowledge is crucial in many fields, from cooking to rocket science. So in essence, reaction theories serve as our roadmap to understanding the speed and mechanism of chemical reactions. Stay tuned for our next segment, where we'll dive deeper into the concepts of reaction rate, order, and molecularity. Now that we've got a grip on reaction theories, let's dive a bit deeper and understand rate, order, and molecularity. First things first, the rate of a reaction. This is a measure of how quickly the concentration of one of the reactants decreases or how quickly the concentration of one of the products increases. The speed of a reaction can be influenced by a variety of factors: temperature, pressure, the physical state of reactants, and their concentration. But for now, let's focus on the concentration. The rate of a reaction often depends on the concentration of the reactants. This relationship is expressed mathematically in what we call the rate equation. The rate equation provides a mathematical model of the reaction, allowing us to predict the impact of concentration changes on the reaction rate. Moseying on to the order of a reaction, it is a term that describes the relationship between the rate of a reaction and the concentration of the reactants. The order of a reaction is determined experimentally and can be 0, 1, 2, or even 3. The overall order of a reaction is the sum of the individual orders of each reactant involved. While order is about the relationship between concentration and reaction rate, molecularity deals with the number of molecules, atoms, or ions that must collide to produce the reaction. This is a theoretical concept, and its value can be 1, 2, or 3, but nothing more. In simple terms, order is an experimental concept, while molecularity is a theoretical one. They're like two sides of the same coin, each providing a unique perspective on the reaction process. It's also worth noting that while order can change with conditions like temperature or presence of a catalyst, molecularity is an inherent property of the reaction and remains constant. From this, we can see that rate, order, and molecularity are essential factors that describe the behavior of a chemical reaction. Mathematics and chemistry might seem like an unlikely pair, but they go hand in hand when it comes to understanding reaction kinetics. Let's start with zero-order reactions. These are reactions in which the rate of reaction is independent of the concentration of the reactants. Mathematically, we express this as rate equals sign K, where K is the rate constant. So no matter how much of the reactant you have, the reaction will continue at a constant pace. It's like a marathon runner who maintains the same speed regardless of the distance they've covered. Moving on to first-order reactions. Here, the reaction rate is directly proportional to the concentration of one reactant. If we double the amount of reactant, the reaction rate doubles too. Mathematically, we express this as rate equals sign K, where A is the concentration of the reactant and K is the rate constant. It's as if our marathon runner now adjusts their speed based on the remaining distance. Finally, we have second-order reactions. In these reactions, the rate is proportional to the square of the concentration of one reactant or to the product of the concentrations of two reactants. We write this as rate equal sign K circumflex 2 or rate equal sign K. It's like a relay race where the speed depends on both the runner's pace and the handoff of the baton. These mathematical equations are invaluable tools in our chemistry toolkit. They allow us to predict the concentration of reactants or products at any point in time during the reaction. By knowing the order of a reaction, we can forecast how it will progress over time and make predictions about how to control it, whether that's in a lab, a chemical plant, or even in our bodies where countless biochemical reactions occur every second. So while math and chemistry may seem like an unusual duo, they actually make a pretty good team. Together they help us unravel the intricacies of chemical reactions, offering insights that would otherwise remain hidden. That's how we use math to predict the behavior of chemical reactions over time. Not all reactions are straightforward. Some are like complex puzzles with multiple pieces, reversible, parallel, and side reactions. Let's start with reversible reactions. Picture a dance where partners can switch back and forth. In a similar way, reversible reactions don't just go in one direction. They oscillate between reactants and products, creating a dynamic equilibrium where the rate of the forward reaction equals the rate of the reverse. This constant to and fro adds a layer of complexity to the reaction kinetics. Now imagine a race with multiple tracks all leading to the finish line. That's a parallel reaction for you. In these reactions, a single reactant can follow different paths to form different products. Each path has its own rate, and the overall rate of the reaction is influenced by these individual rates. So we have multiple reactions happening simultaneously, each adding to the overall complexity. Finally, let's talk about side reactions. Picture a detour on your route that takes you to a different destination. Similarly, in side reactions, an intermediate step in the reaction veers off the main path to form an unexpected product. These reactions can slow down the main reaction and alter the yield of the desired product, adding another level of complexity to our reaction kinetics. But why should we care about these complex reactions? Well, they're everywhere. In biological systems, industrial processes, and environmental cycles, these reactions play crucial roles. Understanding them helps us manipulate reaction rates, control product formation, and even design better drugs or more efficient chemical processes. These complex reactions, while a bit more challenging to understand, add a layer of depth to our understanding of chemical kinetics. So, the next time you see a reaction, remember it's not just A to B. There might be a whole dance, a race, or a detour happening in that tiny test tube, and that's the beauty of chemistry. It's a world of complexity hidden in the simplest of things. We've covered a lot of ground today, so let's take a moment to recap. We started our journey by delving into the fascinating realm of reaction theories. We explored how these theories provide the framework for understanding the mechanisms behind chemical reactions and how they help us predict the outcomes of these reactions. Then we navigated through the concepts of rate, order, and molecularity. These terms aren't just jargon, they're the keys to understanding the pace at which reactions occur, the steps that reactions go through, and the number of molecules involved in those steps. Remember, rate is about speed, order is about sequence, and molecularity is about participation. Next, we dove into the mathematical treatment of different order reactions. We saw how zero, first, and second order reactions each have unique mathematical expressions. These equations aren't just symbols on a page, they're the language that allows us to quantify and predict the behavior of reactions over time. Finally, we explored the world of complex reactions. We saw how reversible reactions can flip back and forth, how parallel reactions can occur simultaneously, and how side reactions can sneak in and alter the main event. These aren't complications, they're the reality of the dynamic world of chemistry, where reactions are rarely straightforward and often full of surprises. But remember, all this complexity isn't there to confuse us, but rather to remind us of the richness and diversity of chemical reactions. Each reaction is a story, and understanding these concepts is like learning to read those stories. So keep questioning, keep exploring, and keep diving into the world of chemistry, because it's a world full of wonder and discovery. And remember, we've only just scratched the surface. There's a whole universe of reactions out there waiting to be discovered. Understanding these concepts is like unlocking the secrets of how and why chemical reactions occur. Subscribe for more, because you won't find me later.